Hi everyone. In this video we are going to cover section 4.1 dealing with related rates. So this is the beginning of our chapter on applications to the derivatives. So now that we know how to take derivatives of lots of functions, how do we use that in like real world scenarios? And so this is the first one that we're encountering. And so what's different with related rates is in this section our variables or our quantities are changing with respect to time. Okay, so instead of like having y as a function of x and taking the derivative of y with respect to x, we're going to have some equation like, I don't know, area of a circle, a equals pi r squared, and we're going to take the derivative of the area with respect to time. And I'll explain how to do this through the various examples. And the derivative of a is 2 pi times r times the derivative of r with respect to time. Okay, so the phrasing related rates comes in because area and radius for a circle, for a given circle, are related to each other. And then rates is we're differentiating with respect to time. So this dA over dt over here, that is how quickly is the area changing as time passes. And then over here on the right hand side, the dr over dt is how quickly is the radius of my circle changing as time passes. All right, so that's kind of the context for what we're doing here. So I'm going to scroll down and we'll get our first example. And in this example, we're inflating a balloon at a constant rate, and that's going to be real important. I'll highlight it actually, to pay attention to when I'm given information. Am I being told a value or a specific radius, or am I being given a rate of change? So in this one, we are given, not the radius is changing, that the spherical balloon is being filled with air, I misspoke a minute ago, at a constant rate of 2 centimeters cubed per second. And so what that means, it's being filled with air, we're changing the volume. The derivative of the volume, dV over dt, the rate of change of the volume is 2 centimeters cubed per second. So it's being filled with air. That's what kind of clues me into we're changing the volume, the rate of change of the volume. All right. And then it asks how fast is the radius increasing when the radius is 3 centimeters. How fast is the radius increasing means we are looking for dr over dt. We're looking for that because it asks me how fast is the radius increasing, changing, when the radius, when r is 3 centimeters. So that's going to be an important part of these related rate problems, establishing what each piece of information that I'm given, like how we represent it. Is it a volume or is it a changing volume? Is it a radius or is it a rate of change of the radius? All right, and then we're going to write an equation that relates all of these variables, and it is the formula for volume of a sphere, of a balloon in this case. V equals 4/3 pi times the radius cubed. And some of these formulas in this section you might need to look up, and that's fine. Okay, but this one we get the volume of a sphere. All right, so once we write that down, the next step is to introduce rates of change to take the derivative. So we're going to write dV over dt, so that's the derivative of volume, is equal to 4/3 pi, that's a constant multiple, and then we're going to take the derivative of r cubed, just like we would take the derivative of x cubed. The 3 in the exponent comes down, r stays the same, and then to the second power. But what we have to remember, and this goes back to kind of the implicit differentiation section, when I take the derivative of r, we also get this factor here of dr over dt. Okay, the derivative of r is dr over dt, but we still use our regular power rule and all that. All right, so I can clean this up a little bit. dV over dt is equal to, let's see, my 3's are going to cancel out. 4 pi r squared times dr over dt. And now, what do we know? We know what the volume is changing at, the rate of change of the volume. We know that 4 is 4 and pi is pi. We don't know what dr over dt is, but I do know that the moment in time that we're looking at this balloon is when its radius is 3 centimeters. And then this is the term that we're solving for. Okay, so I'm going to simplify 2 on the left. Let's see, 3 squared is 9, times 4 is 36 pi, dr over dt. And so then I can divide by that 36 pi and get that dr over dt is equal to 2 over 36 pi, or that is going to simplify to 1 divided by 18 pi. And I'm going to leave that in its exact form. If you get that as a decimal, it's like a really teeny tiny decimal, but I'm going to add on my, not equals, I'm going to add on my units here. This is centimeters per second. If you check the notes in OpenStax, they do use a slightly different notation. And if you prefer that, that's okay. You can use the notation that they use. They write v as a function of time and v prime and r prime. I like the way that I write it, but that is the text that we use, so you can certainly use their notation as well. Okay, so what that value that you just got represents is how quickly the radius is changing as the balloon is being filled with air if you like snapshot it in time at 3 centimeters, a radius of 3 centimeters. Our next slide just gives us procedurally what I did in that last example. Step 1, assign symbols to all the variables in the problem. Draw a figure. We were given one. So that was where I wrote all the information that I was given using all the fancy formal notation. Step 2, state in terms of the variables the information that is given and the rate to be determined. Similar, I kind of did step 1 and 2 at the same time. Step 3, an equation relating the variables, related rates, right? So that's when I wrote down my volume of a sphere equation. Step 4, using the chain rule, take the derivative. All right, we'll often use the chain rule. I didn't mention it specifically, but I was kind of using the built-in chain rule when I took the derivative of the r on the right-hand side. Okay, and the new equation will relate the derivatives. Step 5, substitute everything that we have and solve for the unknown. Notice we're not doing any substitutions until after we've taken our derivative. That's really, really important. Don't substitute before, substitute after you take the derivative. All right, with our next example, you can go ahead and pause the video if you want to read through it and draw yourself a picture. If you look at the notes in OpenStax, they have the picture already drawn for us. But we've got an airplane that I'll draw a crude model of an airplane. This is my airplane, like that, and like that. There we go. It's flying overhead with a constant elevation of 4,000 feet. We've got a person over here somewhere that's looking at the plane, and they're 3,000 feet from the base of a radio tower. So that's 3,000 feet, and they're looking up at the airplane. There we go. Now I want to label my picture, and I'm going to do it the same way that OpenStax did. And actually, my 3,000 feet right here, that's not always staying 3,000 feet, right? Because it says that the plane is flying horizontally away from the man. So that 3,000 feet isn't technically a constant value. It is at the moment in time that we're like looking at this problem, but that plane is always flying further away from the person, but its height is always remaining constant. Okay, so I'm going to leave that 4,000 where it is, and then I'm going to label the horizontal here with an X, and then this slanty guy here with an S. Okay, so this problem is screaming out at me, Pythagorean theorem, right? Do you see the right triangle? I do. That's a right triangle. And it just screams out Pythagorean theorem. All right, but let's write down the information that we know. The plane is flying at a rate of 600 feet per second. All right, so what that is how the horizontal distance is changing. That's the x distance. So that means that the change in the change in x with respect to time, dx over dt, is 600 feet per second. And then the question asks, at what rate is the distance between the man and the plane? So the distance between the man and the plane, this is the man, this is the plane, that's that rate of change. So ds over dt, that is what we are looking for. Okay. I know that x is 3,000. That's like the snapshot in time that we're looking at, 3,000 feet. And the elevation, I didn't give it a variable, but maybe we call it y. Y is 4,000 feet. All right. So the equation that relates the variables of this problem is the Pythagorean theorem. So it's x squared plus y squared equals s squared. All right. Now, if I take the derivative, and I can do that right now, taking the derivative with respect to time, the derivative of x squared is 2x dx over dt. The derivative of y squared is 2y dy over dt. The derivative of s squared is 2s ds over dt. All right, so that looks fairly complicated, but it's about to get better. I want to talk about this dy over dt. Is that 4,000 feet elevation ever changing? The answer is no. Dy over dt, the rate of change of the vertical, the height, altitude of the airplane is not changing. It's 0. So that makes this middle term completely drop out. And I can also divide everything through by 2, simplifying my equation quite a bit to x dx over dt equals s ds over dt. And I almost know all of those things. I know that x is 3,000, dx over dt is 600, ds over dt is what I'm looking for, but I don't yet know what s is. So I need to take a step back for a second and see if I can figure out what s is. Okay, so at this moment in time for my airplane, when the vertical is 4,000 feet above me, when the plane has an altitude of 4,000 feet, excuse me, and the x distance is 3,000 feet, well, I can use the Pythagorean theorem to solve for the distance between the airplane and the man. Okay, so if I go 3,000 squared plus 4,000 squared equals s squared, I know that s is going to work out to be 5,000 feet. So you can check my math there. I'm pretty confident in my right triangle knowledge. But in this problem, we just needed to go out and find one additional piece of information, and it used the same Pythagorean theorem that I already had written down. All right, now we can go back into our derivative formula and substitute in what we know. X, that's 3,000. Dx over dt, that's how fast the plane is going. 600 equals s is, I know now that it's 5,000. And ds over dt is what we are looking for. Use your calculator, multiply 3,000 and 600, and then divide by 5,000, and we find that ds over dt is equal to 360 feet per second. So at the moment that the plane is right above the radio tower, the distance between the plane and the man is changing at a rate of 360 feet per second. All right, now in our last problem for the section, we have water draining from a funnel, from the bottom of a cone-shaped funnel at a rate, there's a rate, 0.03 cubic feet per second. That cubic feet clues you in that that's how fast the volume is changing. It's decreasing at that rate. The height of the funnel is 2 feet, and the radius at the top of the funnel is 1 foot. So we're given the total dimensions of our funnel, and then the question asks, at what rate is the height of the water in the funnel changing when the height of the water is half a foot? All right, so let's start out by drawing a picture, because this one may be a little bit confusing. All right, let's make my funnel white, and I'm going to try to draw a cone, kind of like that. The funnel is leaking, okay, so we've got water pouring out of the funnel like that. Water coming out. Here's the top of the funnel. Again, it's got kind of a cone shape like that. I am not an artist. If you are not an artist, that's okay, but you just do your best. We know that the radius at the top of the funnel is 1 foot. So I'm just going to label a 1 up there. And then similarly, the height from top to bottom of the funnel is 2 feet. That is the total height of the funnel. All right, and so what they say is that water is draining out of this funnel. So there's some moment in time where there is the height of the water is like half of a foot. So let's just kind of draw this as all of the remaining stuff in the funnel. Now, inside of my picture, I'm going to label this distance on the water with a radius of r, and this distance, that's like the water remaining in the funnel, and this is the height of the water that remains in the funnel. Okay, so there's a lot going on in this problem, but this is a good start to understanding what to do. Okay, h is the height of the water that remains in the funnel, r is the radius of the water that remains in the funnel, and v is the volume of that. So the question asks, at what rate is the height of the water in the funnel changing? So we are looking for dH over dt. At what rate is the height of the water changing? Well, that's what we're looking for when the height is half a foot, or if you prefer to write that as 0.5 feet. We also know that the volume is changing, dV over dt, at a rate of 0.03 cubic feet per second, and we're going to write that down with a negative 0.03 because the volume is decreasing cubic feet per second. All right, so there's a little bit of the information that we're given. So next, let's write down our volume formula for a cone, and it is V equals 1/3 times pi times the radius squared times h. Now, before we take the derivative, this is something that's going to be real important to do. I want to refer back to my picture and kind of add on a little bit more to it. Okay, what we can see in this picture is that we have two similar triangles. This first one that is green, and then the second one that I'll make, let me make that one this darker blue. Hopefully that'll be, no, let's use white. Hopefully that's clear enough. There are two similar triangles. And what recognizing that, and this is an important step in the problem, will allow me to do is establish a relationship between the radius and the height. Because I don't want to take the derivative of that volume equation with an r and an h in it. We can, but it gets cumbersome, okay? But what I can do is I can take big triangle over big triangle equals little triangle over little triangle because they are similar triangles. Okay, and so what I mean by that is I'm going to write this down. Let's see. So I've got r over h. This r divided by that h is equal to 1 over 2. 1 over 2. So I'm going, well, I said it backwards, but I went small triangle over small triangle equals big triangle over big triangle. And that's real important because it's going to allow me to just write this volume equation in terms of one variable. So I want to solve this equation for r in terms of h, and we'll do that by multiplying both sides by h, and then we get that r is equal to 1/2 h. And then we'll go like this. We'll go boop, 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 and up here, and substitute that relationship into our volume equation before we ever take the derivative. The 1/2 h goes in for r, and then let's simplify that. Let's see, we're going to have h to the second to the third power. We're going to have a pi again, and then 1/2 squared is 1/4, and then also times 1/3 is 1 over 12. So that took a bit to get to, but we're finally to the point where we can take the derivative of this equation. 1/12 pi h cubed. Okay, if you're still with me, this is a challenging problem, so pat yourself on the back if you are like competent with what's going on. If you want to watch it a couple more times, go for that too. If you are completely lost, send me an email and I'll try to come up with a couple other examples that will help you out. All right, now let's take our derivative, introduce rates of change. dv over dt is equal to 1/12 pi, derivative of h cubed, 3h squared, and then times dh over dt. Let's move this over a bit. I can substitute things right now, but I want to clean this up first. Let's go dv over dt is 3/12 is a quarter pi h squared dh over dt. And now let's substitute in everything that we know. Negative 0.03, that's the rate of change of the volume, 1/4 times pi, and then the height is 1/2 foot. That's the moment in time that we're looking at this this draining faucet, or this draining funnel, dh over dt, and then we solve for dh over dt. So I can multiply by 4, I can multiply by 2, and then let's see what we end up with. If you do that, if you multiply by the 4 and the 2, so multiply by 4 to cancel that out, multiply by 2 to cancel that out, we get negative 0.48 on the left equals pi dh over dt on the right. So then divide that by pi. dh over dt is negative 0.48 over pi, or if I approximate that as a decimal, negative 0.153 feet per second. So the rate of change of the height is decreasing, the height of the water in the funnel is decreasing at 0.15, 15/100ths of a foot per second. Okay, so that's the gist of related rates. So we started with a more straightforward question, got a little bit more complicated, and then this problem got like a lot more complicated. Again, if you want to see more examples, if you have questions, please let me know. That's the end of the section, though. Thank you very much for listening, and have a wonderful day.